Welcome to the problem solving session of the polymer reaction engineering. Now here we will discuss about the various problems related to this reaction engineering concept. Here this particular lecture we are attributing ourselves with the multiple reactions. So let us have the first problem into cognizance. Now the elementary second order reaction we are dealing with having the liquid phase reaction with A plus B equal to C plus D. This is usually conducted in an isothermal plug flow reactor of 1 meter cube capacity. The inlet volumetric flow rate is 10 meter cube per hour, and here the Ca naught is equal to Cb naught, and this is equal to 2 kilomole per meter cube. So under these conditions the conversion of A is 50%. So now if a stirred tank reactor of 2 meter cube capacity is installed in series upstream of the plug flow reactor, then you need to find out the conversion, what conversion can be expected in the new system of reactor. So first let us have a look at what is provided. So it is given that this is the plug flow reactor. Here the volume is 1 meter cube, and V naught is equal to, that is volumetric flow rate, is equal to 10 meter cube per hour. Ca naught is equal to 2 kilomole per meter cube. Then Cb naught is equal to 2 kilomole per meter cube. Obviously because the Ca naught is equal to Cb naught, this is given, and the reaction is A plus B is converting into C plus D, and Xa is, because the conversion is 50%, so Xa is 0.5. So based on the equal stoichiometry of the reaction, this is Ca is equal to Cb. So for the second order reaction, the rate equation can be given as minus Ra is equal to K Ca Cb, or this, because Ca is equal to Cb, so Ra is equal to K Ca square. Now for PFR, the performance equation can be written as tau is equal to Ca naught 0 to Xa dxa upon minus Ra, or tau is equal to Ca naught 0 to Xa dxa upon K Ca square. So this is my equation number 1. Now as it is given that Ca is equal to Ca naught 1 minus Xa, that is my equation number 2. So from equation 1 and equation 2 we have tau is equal to Ca naught 0 to Xa dxa upon K Ca naught square 1 minus Xa square, and it can be represented or rearranged as tau K Ca naught is equal to 0 to Xa dxa upon K 1 minus Xa square. Now this comes out to be 1 upon 1 minus Xa 0 to Xa, and this is 1 upon 1 minus Xa minus 1, or it can be represented as tau K Ca naught is equal to Xa minus 1 minus Xa. That is my equation number 3. Now if given Xa is equal to 0.5, the tau is equal to V upon V naught, V divided by volumetric flow rate at start, 1 meter cube upon 10 meter cube per hour, that comes out to be 0.1 hour, and Ca naught is equal to 2 kilomole per meter cube, which is already given. So if we substitute all these values in this particular equation, we will have 0.1 into K into 2, that is equal to 0.5, 1 minus 0.5, and K is equal to 5 meter cube per kilomole hour. Now if as per the problem, if a new MFR is attached before the plug flow reactor in series, then we may have this type of a reaction stream. Now this is Ca2, this is the second phase, V is given 1 meter cube, and here this V is given as 2 meter cube. This is the Ca1, and these are having the initial conditions which is given in the problem. V naught volumetric flow rate is 10 meter cube per hour. So performance, this is my new scheme. So the performance equation for the CSTR is as we know that tau is equal to Ca naught Xa upon minus Ra, and we can write this tau is equal to Ca naught Xa upon K Ca naught 1 minus Xa. Now if we substitute all the values to this particular equation, keeping in view that for CSTR or MFR, V upon tau is equal to V upon volumetric flow rate at a start, that is given as 2.10, that is 0.2. So if we substitute all the values, then it becomes 0.2 into 5 into 2, that is equal to Xa upon 1 minus Xa square, and that comes out to be 2 into 1 plus Xa square, 2Xa is equal to Xa, and we have this equation upon rearrangement, Xa square Xa square minus 1.5 into Xa plus 1, that is equal to 0. So if we solve this, then we have that Xa is equal to 0.5. Now the concentration at point 1 in the previous equation, that is point 1, this can be given as Ca1 is equal to Ca naught 1 minus Xa, and if we substitute all the values, this is given is equal to 2 into 1 minus 0.5, and that is 1 kilomole per meter cube. So now for PFR, the tau K Ca1 is equal to Xa upon 1 minus Xa, or 0.1 into 5 into 1, that is Xa upon 1 minus Xa, and Xa in this condition is given as 0.33. We have find it out. So we need to find out the concentration at this particular point. So how we can calculate that we will deal in this point, that the concentration at point 2. So Ca2 is equal to Ca1 1 minus Xa, and that is 1 into 1 minus 0.33, and that Ca2 is equal to 0.67. So the overall conversion in the new scheme can be given by the overall conversion in new scheme, that is equal to 2 minus 0.67 upon 2 into 100, and that is 66.7%. That is my answer. Now let us take another problem. Here an irreversible homogeneous liquid phase reaction is carried out with this scheme, that A is decomposes or A is converted into B and C. The reactors are two isothermal flow reactor with a capacity of 50 liter each, and these reactors are operating at a condition of 80 degrees Celsius. You need to find out the exit concentration and conversion if both are operated in series. Now there are two conditions are given. If both reactors are ideal plug flow reactor, and second condition is given that an ideal plug flow reactor is followed by an ideal backmix reactor. Now data is given. the supporting data is given, that is the feed rate is 10, that is v small v naught, that is 10 liter per minute. Now feed concentration, that is Ca naught, is 2 gram mole per liter, and reaction rate constant, that is K is equal to 0.25 minute inverse. So let's have that how we can solve if both reactors are ideal, because the conditions are given that both reactors are ideal plug flow reactor. Now in that case we can have this reactor like this, 1 and 2. Now here Ca2, Xa2, V, and here the Ca1 and Xa1, and here the Ca0, Xa0 and V0. So both plug flow reactors are connected in a series, they are having the same volume of 50 liter. Now if initially feed charging to the first reactor having the concentration of reactant Ca0 and the feed rate V small v0 with no conversion, that is Xa is equal to 0. Now for the conversion at point 1, here at the exit of the first reactor, the performance equation for the first plug flow reactor can be written as tau is equal to V1 upon V0 is equal to Ca0 Xa1 dXA upon minus Ra, that is equation number 1. Now if A is having converting into B plus C, so the rate equation for first order kinetics can be written as minus Ra is equal to Kca or minus Ra is equal to Kca0 1 minus Xa. This is my equation number 2. Now so from equation 1 and equation 2 we have tau is equal to V1 upon V0, that is equal to Ca0 0 to Xa1 dXA upon K Ca0 1 minus Xa, or upon rearranging we can write this as Xa1 dXA upon 1 minus Xa, which comes out to be upon integration, which comes out to be tau is equal to V1 upon V0 is equal to 1 upon K minus ln 1 minus Xa1. So this is, now if we substitute the values which is given in the problem, that is 50 upon 10 is equal to 1 upon 0.25 into ln 1 minus Xa1. Now Xa1 is equal to 0.7135. Now the concentration at point 1, that is the outlet of first reactor, that can be find it out by Ca1 is equal to Ca0 1 minus Xa1, which we have already determined and Ca0 is given to 2. So Ca1 is equal to 0.573. Now this let us term that equation number 3 and this is termed as 4. So if similarly we can find out for plug flow reactor number 2. Now the exit stream from the first reactor become the feed stream to the second reactor with the concentration Ca1. So the initial conversion is Xa1 and the final conversion is Xa2. So both of things we have already find out, that is Ca1 already find it out and initial concentration Xa1 we have already find out. So the performance equation for the second plug flow reactor, this can be tau 2 is equal to V2 upon V0, that is equal to Ca0 Xa1 XA2 dXA upon minus RA. And if we try to solve it, tau 2 is equal to V2 upon V naught, that is CA naught XA1 XA2 dXA upon K CA naught 1 minus XA, or this comes out to be 1 upon K minus ln 1 minus XA XA2 XA1, and V2 upon V1 naught is equal to 1 upon K ln 1 minus XA1 upon 1 minus XA2. So, if we substitute the values to this particular equation, that is given that 50 upon 10, which is already given in the problem, and K is given as 0.25 ln 1 minus 0.7135 upon 1 minus XA2. So, the XA2 comes out to be 0.9179. So, now let us talk about the concentration at point 2, that is at the exit of the second reactor. So, this Ca2 is equal to Ca1 into 1 minus x2. Remember, here this is the initial concentration of for reactor number 2. So, if we put all the values, then we will find that Ca2 comes out to be 0.162 gram mole per liter, because every other things are given in this juncture. So, for two plug flow reactor in series, the volume V1, V2, a single plug flow reactor of volume V is equal to V1 plus V2. So, gives us the same conversion at the exit of as two given is combined. So, if both are having the individual volume V1 and V2, and if they are having the single plug flow reactor, then V is equal to V1 plus V2. So, both are giving the same conversion. Now, to prove this, we have take a single reactor of volume 100 liter and check whether the final conversion and concentration. So, if we take the single reactor of volume 100 liter, now here this is 100 liter. Now, this CAF and this one is CA naught, that is equal to 2. Now, V is equal to 100, V naught is equal to 10, K is equal to 0.25. I am not putting the units of this one because it is quite evident and given the problem. Now, if we write V upon V naught is equal to CA naught 0 to XA dXA upon K CA naught 1 minus XA, or 100 upon 10 is equal to 1 upon 0.25 minus ln 1 minus XA 0 to XA, and if we substitute the values, that minus 2.5 is equal to ln 1 minus XA, then XA find out to be 0.9179. This is the value of XA at the exit. Now, the concentration at the exit of the PFR reactor, which is having the volume of 100, then CAF is equal to CA naught 1 minus XA. We have find out the value of XA. We are having the value of CA naught equal to 2. So, CAF is 0.1642 gram mole per liter. So, therefore, single plug flow reactor of total volume that is equal to 100 liter gives the same conversion as the two plug flow reactor of the volume having V1 is equal to 50 and V2 is equal to 50. Now, let us move to the part B of this particular problem. Here the ideal plug flow reactor followed by the mixed flow reactor. So, here this is my plug flow reactor and this is my mixed flow reactor. Now, here we are having CAF, that is 0.2 and 0.1, and XA2, and here these are the coordinates and the values are given as per. Now the first plug flow reactor, the volume V, the conversion which we have already find out, that is XA1 is equal to 0.7135. Now let XA2 be the conversion at the exit of the mixed flow reactor at point 2. So the performance equation which we can write V2 upon V naught is equal to Ca naught XA2 minus XA1 upon minus Ra, and tau, this is tau 2. Tau 2 is equal to V2 upon V naught, that is equal to Ca naught XA2 minus XA1 upon K Ca naught 1 minus XA2. Now if we substitute all the values, then it becomes the 50 upon 10 is equal to 1 upon 0.25 into XA2 minus 0.7135, already find out this one, minus 1 upon XA2. Now if we solve this XA2, it comes out to be 0.873. So this is my answer to this particular problem. Let us take another problem, that is in isothermal plug flow reactor is designed to give the 60% conversion of A for a second order liquid phase reaction, that is given as A is converting into B. Now pure A at a concentration of 2 kilomole per meter cube is fed to be the reactor at a flow rate of 2.5 meter cube per hour. The rate constant for the reaction at a specified operating temperature is given as 0.25 meter cube upon kilomole per hour. Now when the reactor is actually operated based on this design, it was found that 30% of initial reactor behaved as a well mixed reactor, while the remaining behaved as a plug flow reactor. So you need to calculate the conversion and obtained in such type of a reactor. So it is you can say a mixed type of a problem. So let us have a look of this particular problem in a different mode. Now it is given that A is converted into product and Ca naught is equal to 2 kilomole per meter cube, where you see that Xa is given that 60% of the conversion. That means Xa is 0.60, initial flow rate is given 2.5 into meter cube per hour. Now K is given to 0.25 meter cube per kilomole per hour. Now decomposition of reactant A is in the second order. So we require, we equate the second order decomposition of the reactant A. So this is equal to minus Ra Kca square. Now in terms of a conversion, minus Ra is equal to K Ca naught 1 minus Xa. This is my first equation. So when we talk about the performance equation for plug flow reactor, that is tau is equal to V upon V naught Ca naught 0 to Xa dxa upon minus Ra, or V is equal to V naught Ca naught 0 to Xa dxa upon K Ca naught 1 minus Xa square, or V is equal to V naught K upon Ca naught 0 to Xa dxa upon 1 minus Xa square, that is equation number 2. So if we integrate this equation number 2, then we find that V is equal to V naught K Ca naught 1 upon 1 minus Xa, that is this one, and upon rearranging all these things we find that V is equal to V naught upon K Ca naught Xa upon 1 minus Xa. That is my equation number 3. So if we substitute the given value given values whatever given in the question in this equation, we may find that V is equal to 2.5 upon 0.25 into 2 into 0.60 upon 1 minus 0.60, that is V is equal to 7.5 meter cube. Now, it is given that when reactor operated based on this design, then 30% of initial reactor behaved as a mixed flow reactor and remaining as a plug flow reactor. So, let us redesign the things here. This is your MFR 30%. Now, it is my PFR which handles with 70%. So, initially we have X naught, Ca naught, V naught. Now, the volume for CSTR would be 0.30 into 7.5 and that is 2.25 meter cube, and for PFR that is 7.5 into 0.70 and that is comes out to be 5.25 meter cube. Now, the conversion X1 at the exit of the CSTR in the previous problem, the performance equation can be written as V1 upon V naught, that is equal to Ca naught minus Ca upon minus Ra, and that is Ca naught minus Ca naught into 1 minus Xa upon minus Ra, and tau is equal to V1 upon V naught, that is equal to Ca naught Xa upon minus Ra. That is my equation number 4. So, from equation 1 and 4 we may have this V1 upon naught is equal to Ca naught Xa1 upon K Ca naught 1 minus Xa1 square. So, V1 upon V naught is equal to Xa1 upon K Ca naught 1 minus Xa1 square. That is my equation number 5. So, if we go ahead with this thing, then K Ca naught V1 upon V naught is equal to Xa1 into 1 minus Xa1 square. So, on putting the values for known parameter, we may have 0.25 into 2 into 2.25 upon 2.5. This is equal to Xa1 upon 1 minus Xa1 square, or 0.45 equal to Xa1 upon 1 minus Xa1 square, or 0.41 into 1 plus Xa1 square minus 2 Xa1 is equal to Xa1. And if we calculate this thing, this Xa1, we find that it is Xa1 is equal to 4.2222 plus minus 3.7185 upon 2, and Xa1 comes out to be 0.252. That is taking the negative sign, because it cannot go beyond 1. So, taking negative sign. Now, for conversion at exit of PFR, that is give the performance equation, you can write that tau 2 is equal to V2 upon V naught, that is equal to Ca naught Xa1 Xa2 dXA upon minus Ra, or V2 is equal to V2 upon V naught is equal to Ca naught Xa1 Xa2 dXA upon K Ca naught into 1 minus Xa square, or V2 upon V naught is equal to 1 upon K Ca naught Xa1 Xa2 dXA upon 1 minus Xa square. So, if we go on further rearrangement, then it comes out to be V2 K Ca naught upon V naught, that is equal to Xa1 Xa2 dXA upon 1 minus Xa square. So, upon integrating, we have V2 K Ca naught upon nu naught, V naught is equal to 1 upon 1 minus Xa, Xa1 Xa2. So, V2 K Ca naught upon V naught is equal to 1 upon 1 minus Xa2 minus 1 upon 1 minus Xa1. So, if we put all the known values of the parameter and solve, then we have 5.25 into 0.25 into 2 upon 2.5, that is equal to 1 upon 1 minus Xa2 minus 1 upon 1 minus 0.252, which we have already determined, and that is 2.387 equal to 1 upon 1 minus Xa2, and finally the Xa2 comes out to be 0.581. Now, this is the required conversion at the end of the PFR. So, by this way we find it out for the entire segment. So, in this particular lecture we deal with the various kind of multiple reactors and multiple reaction systems, and if you wish to have further more studies related to these problems, there are couple of references enlisted in this particular slide. You may seek the help of these references for further studies. Thank you very much.